So good morning, everybody. Thank you very much for being here, for having came to this Observatory colloquium that is exceptional on a Tuesday, but I mean, we do whatever we can each time. And overall, thank you very much to our speaker today, Associate Professor Filiz Kahraman, sorry for the pronunciation, Aliçavuş. She's Professor Filiz Kahraman Aliçavuş is Associate Professor at Çanakkale, Onsekiz, Mart University in the Faculty of Science in Turkey. She is a specialist in spectroscopy and the study of pulsating stars and eclipsing binary systems. Filiz Kahraman Aliçavuş earned her PhD in astrophysics in this faculty in Çanakkale Onsekiz Mart University, with a thesis focused on the photometric and spectroscopic study of pulsating stars of type A to F. She completed her PhD thesis also at the Wrocław University in Poland with the support of an international grant. Then she became postdoctoral researcher at Nicolaus Copernicus Astronomical Center, where she involved in the project The Causes of Hot Star Variability and carried out spectroscopic studies of B-type pulsators. She has several publications and projects on the spectroscopy studies of single and or binary systems. She continues her studies in the field of spectroscopic of stellar systems, and she's currently working on a project related to delta Scuti. I look at Eloy. Delta Scuti pulsators in eclipse binary systems. And today, as you know, she's talking about the role of spectroscopy in stellar astrophysics. So thank you very much, Dr. Kahraman, for your accepting our invitation to at least Severo Ochoa colloquium, and the floor is yours.
Thank you. Thank you so much. Before starting my presentation, I just want to say I brought some Turkish delights for you. And maybe you can just help me. And we have a word in Turkey, and eat sweet, think sweet. So it's just a magic before the presentation. And yeah, sure. Please. And thank you for this nice introduction. And today I'm going to talk about the spectroscopy's role in stellar astrophysics. But before starting, I would like to thank two people, Javier Granado and also Giovanni Meu for their invitation, and to the Institute and also Severo Ochoa project for letting me to be here and giving this talk and meeting with these nice people. Thank you so much. Okay, let's start because it is just a very long presentation. Okay, not working. Maybe I can do it here. No, okay. So let's try again. Let me try. Okay, now it works. And she already introduced me. This is my nice university, seaside, and maybe you already know about the Çanakkale. Çanakkale is a very nice place. Maybe you heard the Troy City, and Troy City is there, and it's a unique place because it consists of two continents, half Asia, half Europe, so like Istanbul. And this is an advertisement from my radio program. Actually, everyone to say I'm having a radio program and talking about astronomy. I'm not a professional, but I just try to teach or say something to the public about astronomy because it's the first science and I believe it's important. And so this is the radio station of my university. Okay, let's start the spectroscopy. And today I will try to show why spectroscopy, why it is important. And I will try to show you the cookbook of spectroscopy. Probably all of you know that if a white light goes through a prism or if it rises to a grating, we can obtain this electromagnetic spectrum. So spectroscopy is actually dealing with the spectrum of any object. And in my opinion, spectroscopy is like a kitchen. You must go and eat because it's necessary. And it's necessary to have some atmospheric parameters to really deeply understand the stellar systems or any system. So that's why I think it's like a kitchen. And by doing spectroscopy, you may learn many things about the stellar system or other system. For example, basically you can do stellar classification. What I mean by saying stellar classification, you can estimate, if I talk very fast, please just tell me, you can estimate spectral types, luminosity types, and also obtain some basic atmospheric parameters like effective temperature, surface gravity, and so on. And most importantly, you can have idea about the abundance of this system. And there is another thing spectroscopy actually offers us. If you are not dealing with binary systems, it is impossible to directly know the mass and radius of a system. And mostly we work with single stars. So in that case, spectroscopy helps us because of using this equation. If you know the effective temperature and surface gravity, you may estimate the star's mass and radius. And these two parameters are really important, and mass we know, and also abundance change the lives of a star. And after all, you may try to understand really stellar structure, evolution of Milky Way, and the galactic chemical evolution. And humbly, I will try to show today the cookbook of spectroscopy. And in my opinion, the first thing you should know about the spectroscopy, okay, if you have a star or an object, first thing you should observe it by using spectroscope, and how you can choose your spectroscope. Okay, you would like to do some spectroscopy, but you should get very nice spectra, and this spectra should good for your purposes. So you should ask for yourself, okay, let's start selecting instrument. Which object do we need do we plan to observe? I mean, you should ask by yourself the spectral type. You are dealing with M type, G, F, O, B, and you should ask this because it is related to rotation, and rotation is a key for selecting instrument. I will tell you why later. And also the magnitude is another key, and your purpose. If you would like to have radial velocity curve for a binary systems, and it is important because, of course, everyone wants to have high resolution spectra, but it's not necessary in any case. So if binarity is important, I will tell you later, because here is you should care about the orbital period by doing when you do your spectroscopic observation. And another thing, pulsation. If you would like to do some astroseismology, you need some specific spectra, and plan your observation considering that. Okay, first thing I said that, and also the other things you need, okay, which parameters you would like to obtain at the end of your analysis, spectroscopy. Do you need only effective temperature? So it's okay, you can have low resolution spectra, or maybe you can just do spectral classification. But if you need chemical abundances and do some astroseismology, you will definitely need high resolution and high signal to noise spectra. You see there are many spectroscopes here I listed, and mostly I deal with Filiz, Hermes, and nowadays, and Pharos and US. And as you can see, there are some different kind of spectroscopes with different resolving power. So as I told, everyone wants to have high resolution spectra, but why there is low resolution ones? If we always wanted this, but because this depends of your aim and the objects. And let's just talk about briefly what is the resolution and signal to noise ratio. Probably all of them you know about this. If you resolution is a key to distinguish two close lines between each other. If you have really high resolution, that means you may distinguish two close lines between each other. So, and if we classify the resolving power as low, medium, and high resolution, if a system, a spectroscope have resolving power lower than 5,000, in my opinion, it should be 10, lower than 10,000, but okay. We call this spectroscope as low resolution spectroscope, and for medium, the resolving power should be between these, and for high resolution, resolving power should be higher than 40 or 50,000. And okay, here I give you an example and then talk about the rotation, why we should think about rotation velocity. Okay, these white lines you see, it's a perfect spectrum of a star, it's the same star, and I only changed the resolving power. These red lines are theoretical spectra, and the parameter is the same for each panel, but I only reduced the resolving power. You see, for this top two, it fits, the theoretical red lines fits very well with the observation because it's high resolution spectra. But when I reduce this resolving power, you see it's not matching well. So you should care about this. If you have a slow rotating star, for example, in G star case, you should definitely, if you would like to do some, I don't know, abundance analysis and use the metal lines for the determination of effective temperature, you definitely need medium to high resolving power. But if you have, for example, B-type stars, we know that B-type stars rotates faster, if you consider the main sequence, rotates faster than G-type, F-type stars. So if they rotate fast, let's suppose these two lines close to each other, they will blend because of rotation, make the line broaden. And they will blend. And for this case, actually, you don't need a high resolving power spectrum because these lines will be already blended. So medium to low resolving power would help you to analyze, to understand BO type stars. And we also know that there are little lines in OB type stars. So that's why I'm telling you that just ask yourself, which object do you have? Do you have B-type star, A-type star? If possible, just try to check the literature and learn the rotational velocity, and then choose wisely your spectroscopy. And I will tell you why wisely later. And you all know about the signal-to-noise ratio, and it is important in some cases, especially if you would like to do some isoseismology and abundance analysis. It is necessary to distinguish lines, because if it is like that, if there is so much signal, noise, the error bar will be huge and probably your result will not be realistic. That's why signal to noise is necessary. Here I will show you an application with Filiz instrument. Filiz actually offers 3 resolving power and low, medium, and the high resolution modes. And actually, it is not low resolution mode, but for low resolving power for Filiz is approximately 27,000, medium is 47,000, and high is approximately 70,000. So here it's just an application. Probably most of instrument has the same exposure time calculator, and exposure time is also important parameters when you select your prepare your observation. Here first I choose Filiz low resolution modes. I said it's point source and give the 10 magnitude, and I just consider it's A-type star and give the exposure time. You can change the air mass extension, and I just choose the gray sky. So, and when I say to estimate the signal to noise ratio, it says that if the weather is okay in this condition, I will get approximately 40 signal to noise ratio. So let's increase the resolving power, and in this everything is the same. Exposure time is same, magnitude is same, so it's half of the signal to noise ratio. Because when you would like to have higher quality spectra, you may use a little bit signal. Even if I make it higher, so it's just highest resolving power, it will decrease. And why? Maybe you may ask that, okay, it will decrease, but I can change the exposure time. Of course, you can change exposure time, but if you are planning to apply for a proposal, observational proposal, you know that it's just limited time. And people expect you use the time very effectively. If you just give a very long exposure time and try to observe just 1-2 system, probably your proposal, even if it would be very nice proposal, probably it would be rejected because of this plan. And also you should care about the binarity and pulsation. Because let's suppose you have a binary system with orbital period very short, let's suppose shorter than 1 day. Okay, I will show by my hand, but of course I hope I can do this. Maybe I can show it here. Okay, let's suppose it is shorter than 1 day. If you give very long exposure time, the system will come from here to here. And it's meaningless actually to measuring radial velocity from that data. So you should give your exposure time considering your orbital periods. I think it's better to give exposure time less than 0.1 orbital phase time. So you should care about this. And another things you should be careful. If you would like to do astrosseismology, just check your stars pulsation periods. If you give an exposure time less than your pulsation periods, your data would be useless. It is just also consider this. That's why I said in the beginning, just think about your star's magnitude, okay, and use the time wisely and choose the instrument wisely, considering what you need. And long story short, I can say if you have a B type star, I mean moderate to high rotating star, it could be different type, of course. Low resolution or medium resolution could work for you. But if you have slow rotating star and your aim is doing astrosseismology or determining the chemical abundances, you should choose high resolving power spectroscope. And for astrosseismology, you at least need at least 40 or 50,000 resolving power, and signal to noise ratio preferably higher than 150. So till now, I just basically try to show you which instrument you should choose considering which parameters, considering some basic parameters. And first step of doing spectroscopy is normalization. Of course, before that, there is reduction part, but nowadays instruments gives you the spectra after reduction process. I mean the bias subtraction, flat wavelength calibration, and the other things, but I skipped that part. And normalization is important, especially if you're doing, if you plan to determine your star's chemical abundances. Okay, this is a basic code I just give here. Normally I was using IRAF. It's a very old-fashioned. Still, I prefer to use IRAF because I got used to it. But in this program, in any normalization process, I just want to tell you that just be careful about fitting this theoretical line on the continuum level. Don't fit it inside the hydrogen lines, inside any lines, okay? If you do this, and mostly new students do this actually, you will change the shape of the lines, and then you will get completely wrong results. And if you change the shape of hydrogen lines, probably you will never find the results. So it would completely different. Just be careful about this. And this program is my PhD supervisors, Evan Yamchura, his student, and they wrote this program because we know that the most time-consuming and the important part of the spectroscopy is normalization. And it's very basic code. If you would like to learn, maybe I can show you later. And the other things you should be careful about, the second step is the determination of radial velocities. Maybe you can think that, okay, I'm just dealing with a single system, but sometimes we thought they are single, but they are not single. So just be careful. After having the spectra of your system, just check the spectrum itself and see whether there is another flux from different stars, and then check the radial velocity to be sure that it's not a binary. And to estimate the radial velocities, actually, most used technique is cross correlation. And for this cross correlation techniques, there should be a template. This template should be a standard, can be a standard radial velocity stars. When you type standard radial velocity stars, there are lots of stars you can find, but okay, there is another thing you should be careful. The resolving power and the spectral type of these template stars should be more or less the same. Let's suppose you have a B-type stars, and if you use a template as M-type stars, which is useless, you know, because there is no helium in N-type stars. And also, if you use, I don't know, F-type stars to determine the radial velocities of B-type stars, no, just try to find one template close to your star spectral type, or I generally prefer generating my synthetic spectrum and I use it as a template. Okay, so you can do this. They are just matching the cross correlation techniques is match the synthetic spectrum with yours and gives you the shift in kilometer per second. Okay, then you are ready. Okay, you just do normalization, check whether your system is binary or not. Let's suppose it is not binary. I will tell you, in case of binary star, you should do some more process before starting the spectroscopic analysis. And the first thing you may use, spectral classification. Actually, to do spectral classification, very low resolution spectra would help you. But what you can obtain with the spectral classification, spectral type of the star, I mean it's A, F, or G type star, and luminosity type, is it a giant or I don't know, supergiant or Mason star, and also you may have idea about the chemical composition of your system. Is it more abundant compared to sun or less? So it's very basic technique. And there is a code named MK class and written by Richard Gray, and he has very huge spectral classification book. I really enjoy reading it because it's necessary. I think it's necessary book to read before starting the spectroscopy, because you are just dealing with the lines of each spectral types and understanding the stars itself, and which is really amazing for me, just seeing these spectral lines. Okay, it's very amazing. So anyway, the spectral classification is the basic method to know about the effective temperature or luminosities or chemical composition of a star. And now let's start to learn how to estimate effective temperature, surface gravity, and other parameters of a stellar system. And first thing you may use is this continuum level. After you have observation of a stellar system, you will have this Planck curve. It's like that. And when you fit this curve, this continuum level, as you can see, it starts from 6,000 and ends 8,000. Each curve has different shape because of the depending of the effective temperature. So by fitting that, you can estimate the effective temperature from this spectroscopical, from the spectra of the system. And actually, there is a photometric way, the same way, we call it spectral energy distribution. If you have your stars photometric color, I mean B, V, or a Strontium filter, anyway, after reddening this color, you can plot this flux of the color onto this diagram, the same diagram, and there are some fluxes. I generally prefer to use the cruise flux, and you can just compare your star's photometric flux with the theoretical ones and estimate your star's effective temperature as well by applying some photometric methods. And the other things, actually the basic things, maybe the estimation effective temperature is Balmer lines, hydrogen lines, because they are really sensitive to effective temperature. But here, as you can see, I just show you only the wings of Balmer lines. Why? Because models are not so sensitive, especially the local thermodynamic equilibrium models, not sensitive to the core of mostly core of the hydrogen lines. So if you would like to obtain an accurate effective temperature, you should feed the wings. If you do this first time, don't worry if you don't fit the core. But if you don't fit the wings of the hydrogen lines, so that means you are just doing something, choosing wrong effective temperature. Just change your effective temperature and try to fit these wings. Okay, the other things you may use to estimate the effective temperature of a stellar system, we call it metal line diagnostic. Actually, probably all of you know that, using the Boltzmann equation and Saha equations. Here you see that this is the number, this shows the number of excited elements, and here there is effective temperature. But in Saha equation, there is another thing. In addition to ionized number of ionized elements, there is effective temperature here and also the electron pressure. That means it's related to surface gravity as well. So in the metal line diagnostic, we know that for specific element, here they choose the ion, for the different excitation potential of this specific element, you should get the same abundance. Because the changing level will not change the abundance of an element in the star. So there should be, this relation will be null for the correct effective temperature, for the correct parameters. If you change here, you say they change the effective temperature minus plus 100 Kelvin, but there is a correlation, let's say, and goes downward and upward, and this says that actually effective temperature for these are wrong. You should have the same abundance for the correct effective temperature according to the equation. So you may use this. I deal with A, F-type stars, and the ion elements are more abundant in this kind of stars. That's why we prefer using the ion, but it would be different systems. For example, for B-type stars, it would be oxygen or other things. So it depends on your star. It may change. So the other things you may use is equivalent width. Actually, it is the same method with the metal line diagnostic, but here people measures the area of the line and just compare this. It's of course sign of abundance. Compare it with the excitation potential. So for the correct atmospheric parameters, it should be like that. But there is a weakness of this method because to measure the equivalent width for a specific star, it should be slow rotating star, because you should just measure this equivalent width for these specific elements. If it is iron, the line should be created only by iron, not the blend mixture of the other elements. That's why it's just useful for slow rotating stars. And it's a little bit time consuming, but you can prefer it, still people using it. Okay, let's go to the surface gravity determination. It is another important parameter, atmospheric parameters for spectroscopy. And okay, the first thing you may use is Balmer jump, because at around 361 nanometer, I hope I remember correct, there is a jump, because at that part, all hydrogen elements are ionized. So that's why we see this jump here. And as you can see, for the bottom panel, for the stars around this effective temperature and this effective temperature, unfortunately, using Balmer lines is useless. But for the you see the middle panels, for these stars, it would be useful. Each color represented different surface gravities. So you may use this Balmer jump as an indicator of surface gravity. And another things, okay, I changed this. Another things that you can use is the Balmer lines. It's very useful. I would suggest you, if you start the first time doing spectroscopy, just try to fit and create your own code. It's very easy, because we are just checking the simplest way is just checking this key sequence. So if you have a star generally hotter than 8,000 Kelvin, you may estimate the effective temperature. I'm sorry, surface gravity. As you can see here, up the top, in the top panel, it's just 7. They are all theoretical spectra, by the way. It's 7,000 Kelvin, and when they change the surface gravity dramatically, you see the steps. The shape of the theoretical Balmer lines doesn't change significantly, but for these stars, for 10,000 and 25,000 Kelvin, it's changed. So if you have a star hotter than approximately 8,000 Kelvin, it's a good indicator to estimate the surface gravity as well. For the cool stars, I generally use these lines in my spectral classification. Normally, doing the other process I don't prefer, but you may use this to estimate also the surface gravity for cool stars. And metal line diagnostic is another tool to estimate the surface gravities. As you can see, they changed the surface gravity 0.1 dex, and the correlation will just show some scattering points. So if you have a correct atmospheric parameters, I mean effective temperature and surface gravity, so there will be no relation actually, or maybe the flat relation between these two parameters. People are going to sleep. I know it's hot. Just give me a moment. It's just last 5-10 minutes, sorry. And I just quickly want to talk about the rotation. As I told you before, if a star rotates fast, because of Doppler effect, some parts goes through the us and the other backward, sorry. So that just changed the shape of a line, only the shape, they make it broadener. But you should be careful about this. It will never change the abundance, just change the shape. Okay, and unfortunately, most stars has inclination, and when we generally talk about the rotational velocity, we say projected rotational velocity, and that means real velocity times sinus inclination. So like we say an I. And here there is an example, these black lines, the original observation, and they changed the rotational velocity, and you see the line is here, and when rotational velocity increases and the shape line becomes more broadener, but it will never change the abundance of this line, only to change the shape. Okay, going to the last slides and abundance analysis. For these, there are a few methods actually, but mostly public codes uses spectrum synthesis also to estimate the effective temperature and surface gravity. What spectrum synthesis do actually, they change the parameters. There is a huge space of parameters and generates a synthetic spectrum and compares it with your observation and gives you the result. But you should be careful about this. Please just estimate your star's effective temperature and if possible surface gravity first using the Balmer lines. Then fix these parameters a little bit and estimate the other parameters by using the spectrum synthesis methods. And if you would like to do some abundance determination, it is the same. Please just keep fix your effective temperature and surface gravity, sure about that, and then search the abundances. And to do abundance analysis, actually, you should define which elements actually creates these lines. So for that, we generally use atomic databases. I prefer using the Cruch database. It's most completed ones. And also there is nowadays most public programs using these Vienna atomic line databases. It's very nice. And so what spectrum synthesis do? Well, let's suppose you define this wavelength range, and for a specific effective temperature, surface gravity, if possible, V and I, it's just changed only the abundance of the specific elements, starting from solar abundance, and then by having the best fit, as you can see, it's just perfect because spectra is perfect. I would like to really thank my colleagues for giving me this nice spectra and just making me have fun with this spectra. I really enjoy it. You see, it's just perfect. It's wonderful spectra. So you can have your chemical abundances or metallicities. Okay. Till now, I showed the general spectroscopic analysis steps. But if you have binary stars, what you should do? Because if you have a binary stars and if it is a double-lined binary, so you should apply some other methods before starting all these analysis. And it is really so time consuming, and sometimes you feel tired. I just finished a project related to delta squid stars in binary systems. And after that, I said, okay, I will just work with single stars. It is easy because really this is a huge process, and you need really many data, not just one. If you are working with a single stars, 1, 2 spectra would be okay. But for binary stars case, if you would like to do spectral disentangling, this spectral disentangling is that, okay, when you observe a binary stars, if you see the flux from the both components, of course, to do this, to model this each binary components, you may do disentangling. I mean, from the composite spectrum, applying some methods, you can distinguish 2 component spectra. So you can have the primary and secondary spectra separately. But to do this, unfortunately, you need spectra approximately taken from the each point orbital phase. If you have it, it would be perfect, and the code will work very well. But sometimes you have just a few spectra, and unfortunately, that time it's just not safe way. You can do this, but it's not safe way. So if you have a binary star and if you plan to do disentangling, I'm separating the spectra of each components, please just take the data from approximately, not of course, each orbital phase, and also learn before starting the spectral disentangling, you should know about the flux ratio of your binary components. If you got this information, you may apply some methods, and mostly I use FD binary code, and it's a very easy program. And there is also Corel. I never use it, but it just gives some error. Because of that, I never use it, but you may use. Here, it's just an example. After the disentangling, they got the spectra for the systems, and you may apply all this process that I showed you for each component. There is another method that I do, because sometimes I only have one spectrum. So with this, I cannot do disentangling. What I do actually, for example, for this system, it's a pulsating eclipsing binary showing double lines, radial velocity. I had only 2 fierce spectra, so I decided to just create my composite spectrum, because I have this composite observed spectrum, which consists of 2 components flux. And what I did actually, just generated some synthetic spectra for hot components and cool components, and I have an idea about the flux ratios, and using these flux ratios, I combined these 2 spectra until I find the best fitting model. So for that, of course, you should know the radial velocity shifts as well. And I call it as composite spectrum technique. Maybe it has another name, I don't know, but I generally call it like that. If you have 1 or 2 spectra, unfortunately, you have to use this. Disentangling is not works with this. And the last, maybe one of last presentation is related to astroseismology. We already talked about this, but you know which instruments you need now, and the signal to noise ratio should be higher than 150, and also the exposure time should cover your pulsation period, and also you need many spectra, not just 1, 2. If you would like to do some mode determination for pulsating star, I never done this. One of my friends was doing in his PhD master thesis, and I was just watching, and then I learned from him, and he's now my husband. So and so okay, that's like that. Just take more spectra, 50, 60, 100. It's just necessary to determine the pulsation modes accurately. As far as I know, probably you know better than me, there is a code called FAMIAS doing this process for photometric spectroscopic data. And I just want to show my final work, just to say something. Maybe you heard about the Maya variables. It's a new class suggested as a new pulsating star class. And I was in Warsaw that time as a postdoc. And one day I told my boss that, okay, Jared Handler, maybe you know him. I told him that, okay, maybe we should write a proposal, because it is this type of stars are suggested, and do some spectroscopy and learn whether they are really exist or not. And it was years ago, and then finally we got the proposal accepted by Opticon. It was just the first time because I applied many times, and Jared also applied many times. I don't know what happened, but they accept our proposal. It was very nice. I thank them for accepting that, and finally we published the paper. And here I just want to show you one thing. Okay, at the end we say that there is no Maya variable. It's just short conclusion. I just want to show you that there is a star in this sample with effective temperature approximately 20,000 Kelvin, 10,000 and 8,000. For each of them, you cannot, you can of course, but preferably you should use different atmospheric models. Okay, if you have an A stars, F-type stars, I'm talking about mesocars. Of course, if it is supergiant, things are changing because their surfaces are crazy. So that's why you cannot assume an local thermodynamic equilibrium. So for the stars, here you see, you may assume a LTE model for these stars, but for the other stars, you should think about using the non-LTE models. Here I give you an example, and there is a paper, I don't remember, her name is Nivea, something like that, but very nice paper about this LTE and non-LTE models. And it says that in conclusion, in their paper, they said that if a star has less cooler than 15,000 Kelvin, you may use LTE or non-LTE. There will be no change. But if you have a star higher effective temperature than 15 approximately 1,000 Kelvin, you should use non-LTE models. So in our study, we both use LTE and non-LTE models because we had also stars which has higher effective temperature than 15,000 Kelvin. So this is a star B. I think it's spectral types of B9 something, but it's supergiant. So you see these red lines are observations, and these green dots LTE models, and the red lines and NLTE models. You see the differences. So you should definitely use non-LTE models if you are dealing with this kind of stars, and you see the diagram here. And I think that's my last talk, the last presentation. And thank you again for your patience. And it was very nice to be here. Okay, I hope you visit Turkey too. Thank you.
Okay, time for questions.
Okay.
Thank you.
Thank you. So you enjoy it then?
If anyone has questions, Dennis,
Yeah, so can you say something? What are the latest modern ways to determine microturbulent velocities?
Yeah, I had this presentation for microturbulence, and I noticed that it's just 50 minutes talk, and I just hide it. But you are wishing about having to know
So
about
what's the technique now you use or
to estimate microturbulences? Yeah, I generally deal with A-type stars and F-type stars. For them, my pronunciation will be wrong. I generally estimate macro, the small one, and not the micro turbulences. And for this, I also use the because micro turbulences change a little bit the shape of the deep depth of the line.
depends on the value of micro? If it's high, it can change a lot.
Yeah, but for my stars, microturbulence, the small one, my pronunciation is wrong. I know. I know approximately the value they should be. For example, I shouldn't hide this slide, but anyway.
The question was, how do you measure it? I mean, what's the technique now? I mean, I remember normally you would use equivalent width.
Yeah, I'm
it's the
just
same
checking.
way you use ionization equivalent.
Yeah, also I do this method to estimate the microturbulences. The same method.
So you prefer to use equivalent width?
Not equivalent with excitation potential.
Okay, or
Yeah, I'm just checking the line. Maybe I can show it you later. It's my fault because I just hide it. Sorry.
okay, Eloy?
thank you.
Thank you.
a lot. So, my curiosity is about the Maya variable. There are some hundreds of star catalogued as Maya variable, as you know. Do you think that none of these variable is in this range in temperature? They are beta Cephei star or delta QT star. In your determination of this star or your sample, they are too hot, more hot than expected. They are big Cephei pulsating, or the temperature is cooler than
Yeah, there are some.
catalog is delta QT. Do you think this is for all the star catalog by Valona as Maya variable? I know that you don't like too much the name of Maya variable.
Yeah, I like it actually.
Maybe don't see.
Yeah, we chose our stars. I think it's around the 30 star from the Balonos catalog, and then actually there are some. Most of our sample is inside the delta stability strip, but there are some between this SPB and border and delta security, and they, or I mean maybe beta Cephei to delta security borders. We call them technically as Maya variables, but when there are a few hypotheses suggested by Balona, you know, high rotation, binarity, and we checked all of them, and unfortunately we couldn't say, okay, this could be a real Maya variable, because when we see high frequencies on their pulsation frequency, we could explain them with the rotational shift. So that's why we were not sure about calling them as Maya variables. So this is the reason we considered all hypotheses, and unfortunately couldn't find even one sample that we could call as unique Maya variables. Maybe it's not saying that there is no Maya variables. I think in astronomy it's impossible to say. Maybe one day we can discover, but
this is concerning the EMO pulsate. What do you think about the G mode for gamma doradus in G mode, that they are with temperature in the hot part of the delta QT stability, in the border of hot border of the this is the connection between the SPB star in G mode and gamma dot in G mode classical mode. What do you think about this star in the?
Could be related? SPBs and gamma doradus, hot gamma doradus? You mean?
Gamma doradus in the range in 10,000 Kelvin is too hot to the still for the gamma doradus classical in the cooler part of the.
Yeah, we just I don't know, a few years ago there is a paper we just it's also an idea from optical team. Actually, I sent a proposal and they told me that maybe we should care about the hot gamma doradus stars. And that time we chose some stars and whether to see they are hot gamma doradus or just something wrong with effective temperature. And still there are some hot gamma doradus, but I never checked the relation between the hot gamma doradus and SPB stars that time. So maybe I should check it. I generally do spectroscopy and I learn a little bit about the pulsation from my colleagues. So just maybe my answer could not satisfy you, but anyway, you are right. But by the way, maybe they are just, I don't know, fast rotating SPBs. I have no idea. We should check it. That time we just compare it with the delta scutis to understand the nature. But I know that there are still hot gamma doradus stars showing G mode pulsators. So
We have a question from Rafa.
Thank you.
Thank you.
Do you need to calculate the link darkening coefficient in some of your research?
For spectroscopy, I never use it, but for binary stars, yeah.
Because if, yeah, Antonio Garrett, you know.
Yeah, he already told me, I must talk to him because sometimes, especially if you are dealing with test data or Kepler data for binary stars, it really affects the light curve. So it's impossible to model without considering the darkening. So
And
there is,
gravity- and gravity
yeah,
darkening, no?
the gravity darkening. Yeah, it needs some improvements. That's sure.
Second, do you know a paper by Valona, the last paper from Luis Valona, where he stated that something is wrong in the stellar structure? Because
I missed it.
he found a lot of contradictory result when you put a star in a given position in the edge, and there can be show a completely different signature from astros smaller. He doesn't understand why this happened. Maybe you have an idea.
I should read this paper, probably I missed it. Thank you. And so then I can have an idea what exactly it is.
To be honest, Baluna's papers recently, he's challenging everything.
Yeah, I
He's
know
about to
that.
retire, so essentially that's his living present. You have to.
Well, I enjoy reading
Ciao.
those papers.
Anyway, do we have other questions, Channel?
Yeah, but I mean something about the binary stars when it is entangled the spectra. I'm curious about the mass of the stars. Do you consider very massive stars or
Mass of stars for what?
or disentangle the spectra?
Okay. For disentangling, actually, first I model the radial velocity curve because I need at this mass ratio for this disentangling. So it's necessary, and also mass ratio means the amplitude of the radial velocity curves. It's necessary to do a correct disentangling. So it's related actually with the mass as well.
Okay, but are they very massive? Because sometimes if they are too massive, you have additional.
Yeah, for massive stars, I know there is a PhD student of my ex-boss, and he works on B-type stars, and they are pretty massive, and they show less line. They also pulsates. It's really difficult to do this because you have very less line. Of course, you can apply the disentangling method. It's okay. It's not so much depend on mass, but it's related to the spectrum itself for B or type stars. It's really difficult. Maybe it's difficult for me. Maybe for someone it's easy, but it's really because they also show crazy pulsations. So you cannot distinguish these pulsations whether it is caused by radial velocity shift or pulsations. It really takes time to understand. So.
Any more questions?
Well, if not, let's
I have
thank.
one.
Oh, you have one.
Okay.
Actually, a couple of questions
The only person in my back.
about abundances. So these atomic databases, what are the differences between them? There are differences, different light or?
No, as far as I know, the most complete ones is Kuch line list, because they should calculate the theoretically and all the orbital from one orbital to I don't know this English word. Should jump. So the most complete one, the Kuch, and then the Watt. I don't know the detail about these calculations. So.
Mhm. Okay, and what about solar abundances? You said that you start from solar abundances. but
Yeah, I
solar
didn't
abundances
use
are changing.
Asplund. The final one did this. I used this Asplund solar abundance
Mhm. So the-
input.
If I may, I think there is a comment on the
Yeah,
table.
about databases, because I happen to be involved in one of WALD development and things. So WALD is actually not a database that gives you that provides you first original data. WALD is like it's accumulation of different sources that they pick up the best from different sources. It's like Google. You Google something and gives you on top the most preferred result, most probable answer, right? So while they don't calculate anything, it's a collection. So while contains Kurush, for example, database.
Yeah,
where from Kurush they take the best. So they take, for instance, calculation by Kurush and they check it on the sun or other standard stars, and they propose to the user the most accurate transition parameters, so line parameters for particular elements, right? So
Yeah,
so you can't compare Kurush with WALD because it's absolutely two
yeah, one is theoretical calculation and
so WALD, when people say that they use WALD database and they refer to the original source, it's wrong. WALD was never meant to be like this. And so in this list that you give, so what's the difference between WALD and Kurush? The Kurush gives, as you said, he gives calculated, not only observed, so measured line parameters that people measure in the lab, but he uses these measured parameters to inject it in his calculations, and then he predicts new line lists with more lines included. And these predicted lines are not assumed to be used for accurate spectroscopy analysis unless they are tested with real observation. So Kurush database contains millions, tens of millions of lines that are good for model atmospheric calculations where you care only about mean opacity coefficients. But if you go and to analyze line profiles in details, many of these lines that Kurush provides, they are simply theoretically calculated with plus minus, huge error bars that needs to be tuned on the sun, and this is what people who run WALD, this is what they do.
Thank you.
thank you.
Last call for questions. Okay, let's thank Filiz again.